TJUAV is Thomas Jefferson High School for Science and Technology's Unmanned Aerial Vehicle Club, consisting of 18 active members. This year's competition team members are Don Suzer, Volunteer Safety Pilot, Nicholas Makovnik, Payload Lead and Club President, Krishnan Shankar, Programming Lead, Joshua Pickner, Programming Team, William Black, Programming Team and Webmaster, Alan Su, Electronics Lead, Mia Brashear, Mechanical Team and Club Secretary, Evan Cafaro, Mechanical Team. The team submission to the 2023 SUAS competition is Avalon Mark X, a fixed-wing electric aircraft. For the sake of time in this video, we will discuss technical design and flight readiness testing in combined sections rather than splitting them apart into separate sections.
Avalon Mark X was designed and built to meet the requirements of the AUVSI SUAS competition. Throughout the design and testing, we kept all of our criteria in mind. The general safety of both the aircraft and the payload drop was paramount for us, as was its ability to compete in competition. With the maximum flight distance of between 10 and 12 miles, we decided to aim for 12 miles of flight distance fully loaded. We worked hard to achieve the safe minimum takeoff distance of 500 feet and at least 12 miles of continuous flight, working with multiple motor, battery, propeller, and wing combinations to achieve the optimal pairing for our final configuration. For each test, we considered factors such as voltage droop, flight time, component temperatures, low speed performance, and high speed efficiency. Due to our slow speed flight requirements for payload drop, we wanted wings that could generate significant amounts of low speed lift and low drag at high speeds. We reached a combination where, with flaps detected, in conjunction with our powerful motors, Avalon could take off in distances well below the minimum requirement. These parameters gave us the data we needed to choose the best components and designs for Avalon's specific requirements. Our autonomous flight was continuously improved throughout the year with the addition of more sensors to make it as safe and accurate as possible. We also made sure to meet the regulations set out by AMA and all of its stringent requirements for UASs.
Avalon MKX is the successor to TJUAV's Avalon MK3.5 presented at SUAS in 2022. The completion of a plane design has allowed the team to shift their focus from developing the plane itself to completing the tasks and challenges that will be faced during the competition and optimizing the performance of the plane. This is why the general design remains the same, with the plane containing 4 distinct sections separated by 3D printed bulkheads and covered with foam panels which slot into each bulkhead. While a single-section fuselage was considered, the flexibility and ease of maintenance offered by compartmentalization was preferred, understanding that the plane design will have to change every year to meet new competition requirements. Here is a concise overview of the various sections that comprise the aircraft. Starting with the battery section, the original design contained two 16-amp-hour 6S LiPo batteries to power the motors. However, the new design uses two 22-amp-hour 6S LiPo batteries in series. This change increased the aircraft's effective range by 50%, allowing us to achieve the required range of 12 miles. The camera compartment contains a gimbal and camera connected to the electronics bay for target identification. This will be explained in greater depth in the imaging and ODLC section. The third section is the payload section, which rests under the new wing structure. A major decision and design choice comes with the implementation of carbon fiber wing spars and the new NACA 4412 airfoils. Carbon fiber wing spars were picked over aluminum as a single carbon fiber spar is lighter than two aluminum spars, increasing effective range. The NACA 4412 airfoil was chosen over the alternative symmetrical airfoil after recognizing more efficient aerodynamic properties during wind tunnel testing. As for the payload itself, the single UGV drop mechanism from last year was replaced with 6 small payload drop mechanisms, with one position unused as required this year. The last section is the electronics bay, housing all the systems for general flight and mission tasks. Some examples of the electronics in this section are the Pixox flight controller, Raspberry Pi 4 imaging computer, RFD 900X telemetry radio, and the Ubiquiti Bullet AC Wi-Fi antenna. The eBay houses a 4S 5-amp-hour battery used to power all electronics other than the motors and ESCs. Last year's electronics bay was more hastily put together with an emphasis on expandability, but this year's electronics bay solidifies the components by implementing a PCB design, replacing most Velcro mounting with screw mounts and replacing the individual servo extensions with 3 major cable harnesses with one connector each, running into the front, wing, and tail respectively. It also saves weight and improves ground clearance by removing the large tail cone print and replacing it with a tapered-off foam panel.
Avalon Mark X uses a Sony a5100 24-megapixel mirrorless camera with a 50mm f1.8 prime lens. This results in a field of view of 26.3 degrees horizontally, giving a target about 8 inches across, around 70 pixels of resolution at our intended flight altitude of 120 feet. Flight testing has demonstrated that this is sufficient to classify targets. The lens is a manual focus and manual aperture lens which will have its aperture stopped down to f8 to ensure sharpness in the image and maximize depth of focus. keeping targets in focus regardless of variation in altitude. In order to prevent washing out the colors of the target, the camera will underexpose each image by 2 stops. Testing has shown that in aperture priority modes, with this underexposure, shutter speeds have remained above 1/500th of a second and averaged around 1/2000th of a second in daylight and cloudy conditions, eliminating the possibility of motion blur in each image. The camera is mounted on a self-stabilizing gimbal which keeps it oriented straight downwards, so that the center of the image is the ground location of the aircraft, making target localization easier. The camera will take about 2 images per second while the aircraft flies over the target area, and the onboard imaging computer will download these images for processing. The computer will identify which images contain targets using a YOLO algorithm and transmit the images with targets along with GPS coordinates of the aircraft at the time of taking each image to the ground station. The ground station will classify the target using a computational neural network and identify its location within the image using an additional YOLO algorithm, both of which are currently in development. The location of a target is then calculated using the location of the aircraft and the position of the target within the image taken, and the target identification and GPS coordinates are then transmitted back to the aircraft to determine which payload to drop and where to drop it.
The payload and payload drop mechanism are still currently in development. The leading option is our custom autonomously guided payload, which navigates itself to the ground target after deployment. The system uses a GPS module to determine its location, a servo to tension either end of the parafoil, and an Arduino to control all of the components. It runs a PID algorithm extrapolating the GPS setting from successive measurement points and keeping this aligned directly at the ground target by steering the parafoil. The ground target location will be passed to the Arduino by the plane's main flight computer over I2C before drop, though the serial connection is still in development. So far, we've spent all of our time trying to get the mechanism working in manual flight, controlled by an RC transmitter, and have not yet attempted a target tracking drop, making for about 10 total test drops with 0 successes. We faced complications including the lines tangling and the parafoil stalling because the payload was too heavy. After reducing the weight for testing, we were able to get a well-controlled payload flight and hope to test it autonomously soon. Because of complications with the autonomous payload and its overall higher complexity, we are also developing an unguided version, which would merely take into account simple wind velocity along with an empirically determined drag coefficient to estimate wind drift. Our current drop mechanism is a single MG995 servo which is connected to a thin metal rod that's then pulled out of a hole in the payload, releasing it into freefall. For the final design, we are implementing a version with more of these side by side to carry more payloads. The drop mechanism is the same for both the guided and unguided drop.
Communications. Avalon Mark X uses an RFD 900X on the 915 MHz frequency to send telemetry data such as location, attitude, and battery state back to our custom-made ground station from the PIXOC. Additionally, the RFD is used to upload mission waypoints to the PIXOC. For manual flight, there are 2 redundant RC receivers on the aircraft to remove signal dead zones around the aircraft. These receivers are connected on the S-bus inline of the PIXOC, sending transmitter outputs to the PIXOC for manual flight and allowing the safety pilot to switch flight modes to auto, return to home, or manual takeover. The primary receiver is the RX-6R mounted in the nose of the aircraft, and the secondary receiver is the X-8R mounted in the tail. The transmitter sends signal to both of these receivers on a 2.4 GHz ACC-ST connection. The aircraft also has a Ubiquity Bullet AC mounted in the rear, operating on a 5 GHz frequency so as not to interfere with the 2.4 GHz RC receivers. The Bullet sends captured images and their associated GPS coordinates to a PowerBeam AC over Wi-Fi connected to ground station, and the ground station can reconfigure the camera and capture settings in flight through the PowerBeam. Through frequent flight testing throughout the year, the team has ensured that radios perform well at various ranges and conditions. In 17 autonomous flights, the aircraft has never experienced sustained drop connection over a range of up to 750 meters on either the RFD 900X or the 2 RC receivers, which are the 3 safety-critical radios. The RFD 900X provides a throughput of 500 kilobits per second, which is sufficient for its telemetry and command role, and the Bullet provides a throughput of 40 megabytes per second, adequate for image download. Our flight controller provides ranges of 1.5 and 3 kilometers depending on whether the front or rear receiver are active, and the RFD 900X has a range of 20 kilometers, providing ample margin over the actual ranges required at competition.
Avalon Mark X features a single 10-foot aluminum spar that spans the length of the plane, as well as 2 8-foot spars that support the ribbon truss wing structure. The wing and tail sections were constructed from laser-cut plywood pieces and wrapped in Doculam, a monocoat substitute with a heat iron. The wing features 2 3D printed ribs that double as motor mounts, and the separate flaps and aileron sections are connected by a 3D printed clamp. Other 3D printed components include the nose cone, tail receiver mount, rear landing gear mount, and bulkheads. The plane contains 4 separate component bays for the camera, batteries, payload, and electronics. Each bay is enclosed by foam paneling that slides into slots in the bulkheads. The plane uses a 2-wheel carbon fiber landing gear structure in the front and a VEX omnidirectional wheel in the back. Avalon Mark X is stable in flight, and the thin and slightly undercambered wing shape promotes lift generation at higher cruising speeds. The T-Motor AT7224 190 kV brushless motors are powered by 2 6S 16,000 mAh LiPo batteries that connect to 12S 150 amp ESCs. The motors are secured underneath each side of the wing and use 18 by 10 inch props. The table describes the developmental and flying testing conducted on the plane, including endurance and autonomous flying, as well as tests for takeoff, wing loading, control surface pressure, static thrust, and fuselage stress. Avalon Mark X met the flight performance requirements as specified by the competition rules, and also excelled in meeting the team's stress and load testing criteria. The plane has had 25 flights for a total of 3 hours, 23 minutes.
Avalon Mark X uses an onboard Pixhawk 2.4.8 flight controller running Ardu Pilot for autonomous flight. The autopilot can fly the aircraft between waypoints that are programmed in the custom-designed TJUAV ground control station. The combination of the Pixhawk flight controller and the TJUAV ground station allows for significant flexibility when flying in autonomous mode. To tune the Pixhawk for autonomous flight, the Pixhawk's PID parameters were tuned using the auto-tune mechanism, which banked and pitched the aircraft roughly 20 times each. This gave the Pixhawk the information on how each control surface movement would change the attitude of the aircraft. The ground control station was coded by the TJUAV programming team and is modeled off of Mission Planner. The ground station allows for the ground station operator to quickly change various flight parameters, view image data, display previous flight logs, and track flight statistics. The autopilot and ground control station combination achieves various mission tasks and requirements. The ground station operator can arm and disarm the Pixhawk, can activate the return to home feature, and can add waypoints to the route to fly over targets for airdrop. The operator can also view statistics on aircraft altitude, attitude, speed, and battery level. The autopilot conducted 17 autonomous flights this year. A few minutes of each flight was conducted in manual mode, since Avalon Mark X manually takes off and lands, and the Pixhawk's telemetry data was tested on each flight before switching to autonomous mode. Flights ranged from 5 to 16 minutes, and the average amount of time spent in manual mode per flight was 2 minutes. When the autopilot was utilized, Avalon Mark X attempted an average of 10 waypoints. Avalon Mark X hit every waypoint attempted with an average waypoint miss error of 15 feet.
Due to the difficulty associated with developing and testing an obstacle avoidance algorithm and a lack of required sensors, the team has not attempted the obstacle avoidance task this year.
Now onto the safety, risks, and mitigations. During the development of Avalon Mark X, the risks with the highest severity were injury and incorrect assembly during the construction process. In order to mitigate these risks, the team was taught machine safety before operating heavy machinery and was also informed on how each piece of the aerial system is integrated. To prevent validation and verification risks, major design changes, such as the flaps, were discussed and refined before implementation. In order to prevent catastrophes during flight, the team relied on checklists and pre-flight procedures. For example, power and communication loss were mitigated by checking that the batteries were fully charged and verifying that both the main and redundant receivers were working on the ground. To ensure safety throughout the flight procedure, throttle was cut until the plane was on the runway, and the flight plan was double and triple checked to guarantee that the flight boundary would not be breached. Additionally, all flights were conducted by our safety pilot, Mr. Don Cesar. The team also plans on conducting mock missions to practice timing and prepare for the flight line on competition day.
Avalon NCAM-X has undergone significant full mission testing in a simulated environment, where all expected competition tasks were attempted. 4 full mission tests were conducted with manual takeoff, attempted airdrop, transition to autonomous flight, image capture, manual takeover, and manual landing. All flights were completed within the mission timeline and demonstrated sufficient safety of all systems and verified the aircraft's endurance. The team's full mission flight logs are shown here. During the full mission tests, all waypoints attempted were captured within 25 feet. The team's imaging system was utilized during all mission tests and could adequately detect targets and classify objects. An airdrop was not sufficiently completed to earn points. The team hopes to achieve better than this estimated score as additional adjustments are made to the system.
The overall design goals of the Avalon Mark X consists of 3 parts. First of all, we required 12 miles of flight distance. Additionally, we needed a working payload drop system for this year's competition. And lastly, we needed to adjust our speed without losing much efficiency. In terms of imaging, our setup includes a single self-stabilizing gimbal. By sending images between the onboard imaging computer and the ground station, we can calculate the location of the drop target as well as the payload delivery course. In terms of the airdrop mechanism, we are using an autonomously guided payload. It does so by adjusting a parafoil to steer itself. Regarding communication, the Avalon Mark X includes both an RFD and a PICSOC on board, which sends telemetry data to the ground station. The ground station in turn returns flight instructions. The actual aircraft is constructed using 1 square aluminum tube, which spans the whole fuselage. Additionally, 2 square aluminum tubes span the wing, which is made out of a plywood structure wrapped in doculam. Printed bulkheads separate the plane into different sections, reinforced by foam panels. Our autopilot relies on both the PICSOC and the ground station, running ArduPilot. It navigates the plane through GPS coordinate waypoints. Regarding safety, we have analyzed both the risks related to the team and the risks that may occur in flight. Sufficient steps were taken to mitigate each of the hazards detailed in Section 10. The Avalon Mark X was tested in both manual and autonomous flight modes throughout the whole design process. Finally, we'd like to thank Mr. Schuzer, our test pilot, as well as our teachers. This has been the team from Thomas Jefferson High School for Science and Technology. Thank you for your time, thank you for watching, and we're looking forward to a great competition.